Welcome everybody and welcome to our March 2022 meetup. So Paul, if you could switch on, oh sorry, just admitting someone. If you could go to the next slide, Paul, that'd be great. So welcome everyone to our meetup. The open source satellite program runs regular meetups on a diverse range of topics related to space-based and space-enabled systems, from the deeply technical to matters related to the wider space ecosystem. The open source satellite program has been established by KISP. Our vision for the open source satellite program is to make space more accessible and to promote the responsible and sustainable utilization of space. Through our own personal experiences in designing, building and operating spacecraft, the whole system architecture, we have seen at first hand the utility of small satellites, the ideas they stimulate and the value that they have provided to many sectors and industries. And we can see the future potential for small satellites to influence and to make a positive impact on everyone's lives. The open source satellite program is being developed for the open source community by the open source community. And there are lots of ways to get involved, which I'll speak about at the end of the session. So now to today's session. If you've been watching previous sessions that we've held, you'll know that the last two previous sessions have been on the wider space ecosystem. So today we're changing pace slightly and we're moving to a technical topic related to bus technology that was traditionally used in cars, but an increasing number of satellite manufacturers have now implemented that in spacecraft, the CAN bus. I would like to welcome Paul Madel, our senior software engineer, who has many years of experience working on the space implementation of CAN bus, as well as many other things, to talk about all things CAN. So welcome, Paul. I'm really excited to, really looking forward to this talk. So I'm going to hand over to you now. So.
Thanks very much, Catherine. And great to see everybody. James, I wonder if you could mute your, thank you. So, yes, my name is Paul. I'm a senior software engineer, as Catherine said, and I've got a number of years experience writing embedded software on spacecraft onboard systems. But in that time, I've also had the opportunity to work a reasonable amount on CAN bus and had a look at some of the protocols that are available and that kind of thing. And I thought it would be great to share some experiences with the community, because we're all about trying to share what we know, being an open source program. And I know that there are many small satellite manufacturers looking at CAN bus. If they haven't already implemented it, they're thinking about it. And I thought it would be an opportunity to share what we think is a good implementation of CAN bus and hopefully persuade more people to adopt a particular protocol and to try and try and create a CAN bus or CAN bus subsystems that are interoperable, so that when someone's selling something that's CAN bus, it will automatically be operable with other subsystems. So I'm going to talk about what CAN bus is, why it's a good choice for a spacecraft, and then looking at when things go wrong, what things to look out for, the sort of things that people don't like to talk about, the kind of things where, something went wrong with the CAN bus system and how could it have been avoided. And then talk about some of the high-level protocols, and in particular CAN TS, which is our favored CAN protocol, one that I hope I might be able to persuade people is a good choice. And then I think we'll just be taking questions at the end, which I'm sure Catherine will be able to field along the way. You want to put your hand up, you just want to unmute yourself at the end, that's absolutely fine. So what is CAN bus? It's a computer networking system, similar to many other computer networking systems like Ethernet, but with a number of differences. So with our, Ethernet system as we have it right now, we have on the standard modern Ethernet topology, or the way that the network hangs together, you typically have a switch or a hub. And on CAN bus, you don't have that. There is no switch. It is basically all the different nodes connected to the same set of physical wires and communicating over a bus. So what problem does it solve? Well, back in the 1980s, as early as that, car manufacturers were discovering that they were, wanting to create more and more sophisticated electronic devices on their cars. And when it came to actually connecting these devices together, they ended up with a bit of a rat's nest of cabling, very sort of large amounts of, wiring looms. It was quite complicated. It was difficult to design and to fit all of these wires around your car. And so they thought, instead of having this kind of idea of everything being interconnected on a point-to-point link, wouldn't it be great if we could utilize, some kind of bus technology and connect things in a more bus type idea to reduce the amount of harnessing, to reduce the mass, to reduce the complexity, to reduce the maintenance overhead. And so they created something called CAN bus. It was first developed in 1983, and the first standard was published in 1986 by the Society of Automotive Engineers. And then Bosch was very heavily involved with the development of the early CAN bus, and it published several versions, significantly CAN 2A and CAN 2B. And these are the standards that are mostly used today, particularly, both of them actually. And these standards are freely available. You can download them for free. Then the ISO guys got hold of it and decided to publish a standard set of ISO documents, which you have to pay for, licensed to individuals or to corporations, and they have individual documents for the different parts of the protocol stack, which is relevant to CAN bus. And then in 2012, Bosch released the CAN FD standard, which stands for flexible data rate, allowing for more data in a single CAN frame. And as we'll see later on, that's one of the limitations of CAN bus. So CAN FD is now being widely adopted as a natural successor to CAN. The first car to run CAN bus was a Mercedes W140, and here it is, a lovely car. But we don't really know which satellite was the first satellite to run CAN bus, and if you ask different people, you get different answers. We suspect that it was a satellite that was developed by Surrey Satellite Technologies, but we're willing to be wrong if anybody has some better information. And then Ford and General Motors are now using CAN FD, the latest sort of incarnation of CAN bus, on cars that are produced from 2019 onwards. So it's an active technology, CAN FD. What else is good about it? What is good about it? So it copes well in environments with high levels of electrical noise. It uses a differential signaling technique to reduce the effect of noise on the transmission lines. As a priority-based access to the bus, which I'll explain in a moment or two. It has built-in error handling and recovery schemes. It works well under real-time constraints. So if you need data to be passed from one place to another within a particular time frame, then it can be a good choice for those kind of use cases. And it has thought through collision handling. So it handles collisions on the bus without the need for extra software to handle those sort of situations. It's multi-master, so many nodes on the bus can instigate, or any node on the bus can instigate traffic at any time. It's multicast, so a single node on the bus can transmit data and multiple receivers can receive that data. It also supports broadcast, so one node on the bus transmitting data to all other nodes on the bus. And it can also be used as a point-to-point method of communication where one node communicates with another node in a point-to-point fashion. It also has many of the CAN controllers have message filtering, and that is very handy. So it means that the software only needs to handle the messages relevant to the node in question. So if you, for example, on a car, if you had an ECU, an engine management unit, then maybe it's going to be interested in the pressure on the accelerator pedal, but it's not so interested on the volume of the stereo. So it could be filtering out that the software running on that ECU can be configured so that it completely ignores the messages from the radio and is only seeing the messages from the accelerator pedal, for example. And it only requires 2 wires. Where are the limitations? So each CAN frame is limited to being 8 bytes long in the CAN 2 standard, or 64 bytes long in the CAN FD standard. There is a high frame header footer overhead on each data frame that is transmitted. So the amount of data that you can transmit in a frame compared to the overhead of the header and the footer it means that there's a relatively large overhead. The maximum bit rate is either 1 megabit per second for CAN 2 or 10 megabits per second for CAN FD, but some CAN FD transceivers actually go further than that, and I've seen transceivers rated up to sort of 15 megabits per second for CAN FD. And one of the other limitations that you really need to be aware of if you're thinking about getting involved in the world of CAN bus is that not all CAN-enabled equipment can talk to one another. And that is because on top of CAN bus, you need some kind of high-level protocol. And there are lots and lots of competing standards out there. There are this CAN Open, which is used a lot in industrial equipment. There's SAA J1939, which is used a lot in the automotive industry. There's ECSS CAN. This is ESA's CAN network specification, which is actually heavily based on CAN Open. And Skylabs have a CAN implementation called CAN TS, and that's the one that we really like. I'll explain why later. LibreSpace Foundation have created something called Space CAN. And ARINC, which are the standardizations organization that works primarily with the aerospace industry, have an ARINC standard for CAN bus, a high-level protocol called CAN 825. So this is just a snapshot of some of the high-level protocols out there in the industry. There are many, many, many more, and many bespoke ones as well. So when we came to create the open source satellite, we knew we wanted to use CAN bus, and I'll explain why it's a good thing to use. But we needed to figure out what would be a good idea as a CAN high-level protocol. So it's well suited for the interconnection of modules on a spacecraft. It's well suited for the broadcast of time data, for the transmission of commands between modules, for the transmission of telemetry between modules, for the passing of bulk data, although where you're going to use it for this use case, you need to understand that it is a bus and it's a shared resource. So there is it has a limited throughput, and it can be quite slow. So, you know, if you're going to use it for high bandwidth, or need for high bandwidth, it's probably not the best solution for, let's say, streaming video or something like that. But it's also good for broadcasting the synchronization messages. So, for example, on your spacecraft, if you're running a control loop which involves several modules, you might use it to synchronize the beginning of the control loop for attitude control, for example. So how does it compare to other buses? So there are many other bus technologies out there. MIL standard 1553 has been around for a very long time. It's used on larger satellites predominantly because it's very high. It uses quite a lot of power, and it's a strict master-slave arrangement. You have bus controllers and remote terminals, so it's not as flexible in that regard. RS-485 isn't really so much a protocol standard. It's a specification of a physical layer, but many people use a universal asynchronous receiver transmitter over the top of a RS-485 bus to do the kind of things that CAN bus does. But collisions are more of a problem there. So where you have to deal with collisions between messages on an RS-485 bus, and you have to be careful about the protocol that you use on top of the RS-485 to reduce the number of collisions that you'll see. SpaceWire is not really massively comparable. It's a star topology. It's much higher bandwidth, but yes, it's not really a bus, so to speak. RS-422 is point-to-point, not really a bus. And I2C is used a lot now on CubeSats in particular in the new space industry. It's not differential signaling, so it is subject to noise and grounding issues. And I know that many people within the CubeSat sort of sphere are finding these problems with the use of I2C. There is a differential I2C now. It's relatively new as an idea, but to have a differential signaling on I2C signals. But what we've discovered is actually those ideas draw more power than the equivalent CAN bus. So a high-level description of the components of a CAN bus, marrying it up against the OSI model for a communication stack. So at the bottom you have the physical layer, and on a CAN bus that's physically just two wires that are twisted. And at the end of the two wires, you have 120 ohm resistors as terminators. Above that, you have a CAN transceiver, which is a device that takes those CAN signals on the CAN bus and translates them from a differential signal into logic levels that could be understood by a CAN controller. So 0 to 5 volts, 0 to 3.3 volts, that sort of thing. And then in the data link layer, you have a CAN controller. And a CAN controller is generally implemented in digital logic, and it has the responsibility to do the framing of a CAN frame to ensure that the CAN receiver is synchronized with the bus traffic, and to deal with error conditions. And then you have above that, you kind of bypass network transport session and presentation layers generally, although there's some debate about that. And go up to the application layer. And the application layer is generally implemented in software. And the application layer is where you have this high-level protocol implementation. And on the open source satellite, we are hoping to use STM32H7 processor. So in our case, the CAN controller is actually built into the microcontroller or microprocessor, and in fact, the microprocessor has two CAN controllers within it. But there's no. There are varying ways in which CAN buses can hang together. The CAN controller can exist outside of the processor as a bit of digital logic in a separate chip. Or sometimes the CAN transceiver and the CAN controller are actually housed within the same chip, and there's a separate processor. But in our case, this is how we're sort of using CAN bus. So some of the features of CAN bus, which make it a bit interesting, I guess. One is the frame prioritization and collision handling. So I'm going to try and illustrate that with a few little bits on this slide. So let's say that you had two nodes on the CAN bus, and we're in the bad situation where both of these CAN nodes are trying to transmit data at the same instant in time. One of them is transmitting a CAN frame with an identifier, which is the first field that is transmitted within a CAN frame, with an identifier of 257, the number 257. And another one is sending data with an ID of 256. So these nodes are transmitting, and this node over here is not transmitting, it's receiving, it's just listening to the CAN bus. So as the identifier is transmitted, it's transmitted from most significant bit to least significant bit. And the identifier can either be 11 bits long or 29 bits long. That's the difference between CAN to A and CAN to B. So in the case of it being an 11-bit identifier, I just chose that to make these graphics a little bit simpler. Essentially, you'll have node 1 transmitting a 0, because 257 on the 11th bit is 0. And node 2 will also be transmitting a 0 at the same time. And on the bus, what will be seen is what's called a dominant bit. So a 0 translates to dominant on the bus. Now, as these bits are being transmitted by both nodes are not only transmitting, but also looking at what is on the bus. They're observing what is happening on that bus in that bit time. So this node will see that it is transmitting a dominant bit, and it sees that a dominant bit is on the bus. So that's its green light to carry on transmitting. And this one at 2 will be in the, doing the same thing. It's got the green light to carry on. So they move on to the next bit in the ID field that is being transmitted. Again, these will be zeros in the case of 256 and 257, and will be translated as a dominant bit. So both nodes transmit a 0 and see a 0 on the bus, or a dominant bit. And so that's their green light to carry on, again, to keep on transmitting. The next bit for both of them is a 1. And in this case, the bus goes into a recessive state. So the bus can either be in dominant or recessive state. So when the bus is in recessive state, i.e. when everything on the bus is transmitting a 1, then both nodes will observe they're trying to transmit a 1, they're seeing a 1. Again, but they will both attempt to carry on transmitting data. And this will carry on all the way until, in this case, the very last bit. On the very last bit, this node will transmit a 1, this node will transmit a 0. In which case, the 0 takes precedent. That is the dominant state. So what this node will see, node 1, it will see that it's trying to transmit a 0 and it's seeing a 1. At that point, it will stop its transmission. It will back off. It will become a receiver. And it will then hold off until the next opportunity it has to send the CAN frame that it was trying to transmit. And the beauty of this mechanism is that the node 2 has overcome any collision without the need of actually transmitting all the data, observing a collision, and then having to deal with it in some way. And this happens without any software intervention at all. This all happens down at the sort of close to the physical layer, at the data link layer within the CAN controller. So that's a big plus for CAN bus. Another feature which exists on a CAN bus is the way that it acknowledges traffic on the bus. So let's say node 1 is transmitting, again, 257, an ID of 257. And these two nodes this time are just listening, they're receiving data. So as time goes on, these bits of the CAN frame are transmitted one after another. And some way through the transmission is an ACK bit. And when the transmitter sends the ACK bit, it puts the ACK bit, as a recessive bit. Now, what happens is that the receiving nodes actually change the state of that ACK bit into a dominant bit. So that is then read by the transmitting node, so that the transmitting node knows that something else on the bus that is listening and is happy with the frame that is being transmitted has acknowledged that that frame is on the bus. And so it knows that that CAN frame is gone somewhere, and therefore at the end of the transmission it terminates the transmission. If the ACK bit is not set to the dominant state, so if the node 1 on reading the ACK bit that it's trying to set recessive sees recessive state, it will actually continuously try to transmit this frame over and over again until the ACK bit is the ACK bit is set to a dominant state. So I've talked a little bit. I said that it was good for time distribution. A lot of the CAN bus high-level protocols that are out there, particularly in the space segment, have use a high priority message ID, typically 0. So for the transmission of time around the system. Now, if you do that, then that is going to be the highest priority message on the CAN bus. So if you use that mechanism, then actually you can have a known latency between the time that you wanted to send the time across the bus to the point where the receiving nodes have received it. So you could broadcast your time message across the CAN bus and know when it's going to be received. So you have a known latency. The minimum latency, if you had a CAN bus running at 1 megabits per second with a 29-bit identifier and assuming some other bits and pieces, the minimum latency is 75.8 microseconds and the maximum latency is 196 microseconds. So it's not a large amount of jitter, and it is quite good for that use case. Typically, most satellites these days use a pulse per second interface, so point-to-point links or some kind of bust pulse per second signal to transmit the notion of time around the spacecraft. The beauty of this method is it doesn't really particularly add much in terms of latency, but you also get the benefit of actually having transmitted the time with the indication that this is the start of a second. So when things go wrong, and this is of interest, so one of the issues that you can have in a space application is a single event upset, whereby cosmic radiation causes a bit flip in your silicon and means that your registers on your microprocessor may flip state. Now, in the case of CAN bus, a corruption of the bit timing registers can have a pretty bad effect. I'll explain why. So coming back to this frame acknowledgement, let's say node 1, let's say all the nodes are configured to 1 megabit per second. And then something happens. There's a single event upset in node 1. And now node 1 is going to be transmitting data at 500 kilobits per second, let's say. So half the data rate. As it transmits data, it's going to be transmitting it, the bit timing of this message will be half that it should be. And all of these nodes will be expecting data at 1 megabits per second. They will not recognize the CAN frame and they will not set the ACK bit to the dominant state. Now that means that node 1 will continuously and constantly transmit data on the CAN bus forever, according to CAN protocol. Now, many of the CAN controllers that are out there give you the ability to prevent, to stop that continuous transmission. And so that's one mitigation that you can use to prevent that from happening. Maybe have some kind of timeout, that stops the transmission after a certain amount of time. Or another mitigation is to continuously refresh the bit timing registers so that the problem can effectively get fixed. But sometimes that can lead to some other problems, needing to switch the CAN controller into an initialized mode in order to change the register values, for example. Another problem that can arise is where two frames on the same bus transmit a frame with the same ID. So coming back to, coming back to this scenario where you had two nodes and they were transmitting messages with different IDs. If these IDs are the same, this frame prioritization and collision handling mechanism, which is part of the CAN protocol, doesn't work. And so both frames will end up on the bus fighting when it comes to the data field, which follows this ID. So yeah, just going back to the frame format, there's the message ID and here's the data. So, both frames will end up over here somewhere and both nodes will attempt to transmit all of this data, causing actually undefined behavior. What we've seen of that behavior in terms of CAN bus protocol is that it can lock up the CAN bus. It can cause the CAN bus to lock up and you have to sort of either reset the CAN controller, do something fairly fundamental in order to recover the situation. So when we came to the open source satellite program, one of the key things we were looking at was to ensure that when we choose a high level protocol on top of the CAN, we must choose one that ensures that that can't happen. And we've been doing a collaboration with ISIS Space, and some of my colleagues from ISIS are on the call. to try and further work on CAN bus. And part of that has been ISIS looking at the physical layer and coming up with a demonstrator, writing software to demonstrate a CAN network on the hope that they might be able to implement that on their spacecraft going forward. And for us, obviously, it's the same sort of thing. We want to be able to do the same thing, and we figured it was a good opportunity to collaborate, because the more people using the same standard means that there's more interoperability. So part of that collaboration was to look at some of the high-level protocols, and we looked at a number. First one was J1939 that we looked at. That's a very widely used protocol on automotive vehicles, trucks, cars, that sort of thing. It supports CAN FD, the faster variant of CAN bus. It doesn't have redundant buses, so as part of the standard, a lot of the space standards have a notion of a redundant CAN bus. So 2 CAN buses where you'd normally have 1. And the message formats are largely based on automotive data. So the identifiers for the frames are sort of reserved for, let's say, I don't know, brake pressure or car things. So another one we looked at was Skylab's. They produced they've got a lot of experience with use of CAN bus in space, and they produced a stripped down CAN protocol called CAN TS, and this we think is very good. We wrote some requirements that we wanted to assess these protocols against, and this hit nearly all of the criteria. It is open source. The standard is open source. It's a simple protocol and fulfills most of the requirements that we had. If you want to see the requirements that we were working to, you're more than welcome to, we'll distribute those to you. It has some flight heritage. It's flown on a number of missions, and the link to the Git, they have their own GitLab, which they've made public. There's an example implementation and some documents that describe the protocol on there. Then we looked at CAN Open, which is a very, it's used a lot in industrial equipment on the ground. It's very widely adopted. It does support CAN FD. It's an open standard. Unlike J1939 is not so much of an open standard, by the way, but CAN Open is, hence the name. Redundant buses are not part of the standard, and I've found it quite complex and difficult to understand. I know it's not just me. That other people have looked at it and had to scratch their head quite a lot to understand what's going on. So it's not very easy entry, and also it has quite a large footprint on the code that is running the protocols. So then we looked at ECSS CAN, which is the European Space Agency's variant of CAN bus. Now, basically, that's exactly the same as CAN Open, except it introduces a redundant CAN bus, and it's good, but it hit a lot of our requirements, but it is quite complex and is not very suitable for memory constrained devices. If you want to run a CAN bus with an 8-bit microcontroller, it might be a bit of a struggle with some of the aspects of this protocol. Not all of it, but there are certain aspects which will cause you some issues. Then there's LibreSpace. They've come up with a protocol called SpaceCAN. It's an open standard, a simple protocol. It was missing some of the features that we were looking for in terms of the requirements that we generated, and is actually has a is susceptible to that problem I was talking about, where two nodes on the bus transmit data with the same ID at the same time. That is a vulnerability that is there with this CAN protocol. Then we looked at something else which is quite common on CubeSats called CSP, which started life being called CAN Space Protocol and has been rebranded CubeSat Space Protocol. It started off as a sort of protocol on top of CAN bus, and now it covers different aspects. So it's been extended to other serial bus technologies and communication from the ground to space as well. It's an open standard, simple protocol, but it has a high data overhead. So if you want to send much more than 1 byte of data, then typically you have to send 2 CAN frames. So there's quite an overhead there with the transmission of data. It's not very well documented. When I've tried to understand it, I've had to look down to the source code to on a GitHub called libcsp. There's some information there. There's some diagrams. There's some information, but in terms of how the protocol hangs together, it can be quite tricky to understand. CSP2, which exists, as I understand, it's not very widely adopted at the moment, but it's not backwards compatible with CSP1. So it's something else to consider. So the conclusion of our looking at different CAN space protocols is that CAN Open hit most of our requirements, but it's too complex and too large a memory footprint for small embedded targets. Space CAN is smaller, simpler, but contains vulnerabilities. J1939 is basically too automotive focused. CSP has been adopted, is not backwards compatible, and has a high data overhead. Now, CAN TS is small and simple and hits nearly all the requirements except for support of CAN FD. I've also since found through talking to other partner organizations that there is one at least that I've found that I've actually adapted CAN TS to run on a CAN FD network as well. But I don't think there is any CAN FD variant, CAN TS variant that supports CAN FD in a sort of published standard, if you like. With that, thank you very much for listening. I hope this was useful. And if you're thinking about CAN networks, you want to use a CAN network, please use CAN TS because we want to have as many subsystems out there that are compatible with the open source satellite as possible. Please, that would be great. So that's my preach. That's my message. And I hope this has been useful if you're thinking about adopting CAN bus. And I'll now hand over to Catherine. Thank you very much.
Okay, thank you, Paul. Brilliant. That was really highly informative. I know I've learned a lot about CAN bus. And I understand a lot more about how it works. Is there any questions at this point from anyone on the call? Or have you completely bamboozled everybody? Anybody? Okay. Right. Well, brilliant. So thanks a lot. Yes. So yeah, moving on. So thank you for joining us today. If you are interested in the open source satellite program, there are a number of ways you could get involved. You can simply sign up and get updates on what we're doing. You could look to contribute on some of the projects which span things like software, hardware, or even marketing activities. You could participate in or mentor or judge some of our design-a-thon activities. If you're working on a mission or considering even developing a mission, you could be an early adopter of what we're doing. Or you could even get in touch and give a talk like Paul has done today on an area of interest. We're always looking for more guest speakers to come and talk to us so we can find out add greater dimensions and perspectives to the work that we're trying to do in the industry. So please, if you are interested, do get in touch. Or you could sponsor us. Contributing to what we're trying to do will enable us to go faster with our developments. I do notice in the chat a question has popped up. So so Josh is interested in single event upset ideas. So do you have any comments on that at the moment, Paul?
Yeah, so if I go back to where I was talking about that, yeah, where things go wrong, yeah. Certainly, as I said, if you have a single event upset in a very unfortunate place in a bit timing register, then you will see the transmitting node switch to a different baud rate, which won't be picked up by the other nodes. So there are two ways of that I can foresee that you can resolve that issue. One is to continuously refresh those registers so that they are constantly being told, you're transmitting at 1 megabit per second, you're transmitting at 1 megabit per second. In which case, if there is a single event upset, it would be resolved by the refresh of the registers sort of actively, so the problem goes away. The other way of doing it, which you can work alongside that, is to ensure that if you begin a transmission of a CAN frame, so if I come back over here, so if you're transmitting a CAN frame, and then you see at the end in the software that the software is aware that that CAN frame is being retransmitted again and again and again. So there'll be in the CAN controller, there'll be some indication that the transmission was successful or ongoing. So if the transmission is ongoing for a fair time, let's say half a second or something, the chances are something bad is happening, and you should stop transmitting on the CAN bus. So so you could configure the CAN controller to stop that transmission on the CAN bus at that point in time, so that you at least give the chance for the other nodes on the bus to carry on talking. So those are the sort of two ways that I've seen that mitigation being put there. Is that helpful, Josh?
Right.
Great.
Fantastic.
And then I think Etienne.
Okay. I'm not sure if they're still on the call, actually. I think they've gone. Okay. Right. If you'd like to move back through onto the slides.
Sure.
That would be great. So next month, go to the next. Next slide. Oh no, that would be perfect. Thank you. So next month, because we're doing this on a monthly basis, we'll be looking at a system engineering topic close to our senior system engineer's heart, Vicky Anderson, and she's going to talk about model-based system engineering. Vicky, would you like to give a quick taster?
I can indeed try. Thank you, Catherine. Though Paul's given me quite a lot to live up to, so I feel a little bit fresher now. So what I'd like to talk about is kind of what is model-based system engineering, because it's probably a phrase for some people that they aren't aware of, and why would you want to use it? What are the benefits over what we'd call sort of maybe traditional engineering techniques, and how is it helping us on OSAT? What is it giving us that actually makes it a worthwhile cause and something that you guys should be interested in? So yeah, that's a very high level, and I have to come up with a snazzy title like Paul. I think my model-based system engineering title needs some pizzazz, so I will give that some work between now and next month.
Okay, thank you, Vicky. So yes, so that's next month on Thursday, the 21st of April, and that'll be at 4:30. It says GMT. I should replace that because I will be on British summertime by then, so it will be BST. Do watch out for that. Adverts will appear in the usual places, so do please sign up. That'd be fantastic. So many. Can you move to the next slide, Paul? Thank you. So many thanks for your time and attention today. It's been a great pleasure to see many of you on the call. So hopefully we'll see you next time, and thank